Hello everyone, myself Professor Venkat Ghodke. I am associated with ENTC Engineering Department of AISSMS, Institute of Information Technology. In this video, I am explaining you time varying electromagnetic field. Here, stationary charges, electrostatic field, steady current, magnetostatic field, time varying current, electromagnetic fields. Only in a non-time varying case can electric and magnetic fields be considered as independent of each other. In a time varying field, that is dynamic case, the two fields are independent or interdependent. A changing magnetic field induces a electric field and vice versa. Here the continuity equations. Electric charges may not be created or destroyed according to the principle of conservation of charges. Now here we will consider an arbitrary volume bounded by a surface. A net charge Q exists within this region if a net current I flows across the surface out of this region. The charge in the volume must decrease at a rate that equals the current. That is the relationship between the current and current density I is equal to the integral of j dot ds, that is equal to the minus dq by dt, that is equal to the minus d by dt integral of rho v dv. According to the divergence theorem, integral of del dot j dv is equal to the minus of integral of dou rho v by dt into dv. This equation must holds regardless of the choice of the volume v. Therefore, the integrand must be equal, and partial derivative because may be a function of both time and space. That's why the divergence equations minus integral of dou rho v by dou t and dv. Now here the del dot j is equal to the minus dou rho v by dou t. That is the equation of the continuity measured in ampere per meter cube. And the Kirchhoff's current law follows from this equation called as the del dot z is equal to the zero. That is steady electric current or divergence or solenoid. For a magnetostatic field, we recall that the equation del cross H is equal to the J. Taking the divergence of these equations, we have del dot del cross H is equal to the del dot C, that is equal to the 0. However, the continuity equation requires that the del dot J is equal to the minus dou rho v by dou t, that is not equal to the 0. Thus, we must modify the magnetostatical equation to agree with the continuity equation. Let us add a term to the formal so that it becomes del cross H is equal to the J plus JD. And we know that J is nothing but the current density and JD is nothing but the displacement or conduction current density. Now here the J is equal to the sigma E. Capital E is to be determined or defined. Now here we can taking the divergence, we have del dot del cross H is equal to the 0 del dot J plus del dot JD. Therefore the J del dot JD is equal to the minus of del dot J. In order for these equations to agree with the continuity equations, so del dot JD is equal to the minus of del dot J is equal to the dou rho v by dou t is equal to the dou t in bracket del dot D and del dot dou d by dt. Therefore, the ZD is equal to the dou d by dt. So, equation is del cross H is equal to the J plus dou d by dou t. Therefore, here the del cross H is equal to the integral of del dot H del cross H dot ds is equal to the integral of J plus dou d by dou t dot ds, that is nothing but the Stokes theorem. Now here the displacement current is continue. A typical example of the displacement current is the current through a capacitor when an alternating voltage source is applied to its plates. The following example illustrates that the need for the displacement current. So using the unmodified form of the Ampere's law, integral of H dot dl is equal to the integral of J dot ds is equal to the I enclosed is equal to the I is equal to the dq by dt, that is also I enclosed is equal to the 0. So we know to resolve this conflict, we need to include in Ampere's law. So Faraday's law discovered experimentally that a current was induced in a conducting loop when the magnetic flux linking the loop changed in differential or point form. This experimental fact is described by the following equation: del cross E is equal to the minus dou B by dou t. Taking the surface integral of both the sides over an open surface and applying the Stokes theorem, here we obtain the integral of E dot dl is equal to the minus dou d dou by dou t integral of b dot ds, that is equal to the minus psi dou psi divided by dou t, and dou psi is nothing but the magnetic flux through the surface S. Now the pointing theorem is an identity based on Maxwell equations, which can often be used as an energy balance equation. Now here the Faraday's equation is del cross E is equal to the minus dou b by dou t. Ampere's law is del cross H is equal to J plus dou d by dou t, and the vector identity will be the del dot E cross H is equal to H del cross E minus del E dot del cross H, and del dot E cross H is equal to the minus H dot dou B by dou t minus E dot dou D by dou t minus E dot J. So thank you very much for watching this video.